So welcome to the computer graphics practice video, and this task we'll be discussing the shader chopper. So in this task we'll try to make the chopper from the previous task have this gradient coloring. Now in C++ you can continue from the previous solution for either the cube chopper or client chopper exercise, and that solution already has much of the things required already done. So JavaScript people will write a whole lot of additional code in this task. C++ people already have most of it there. So this is why the task asks you to explain different keywords for different shader variables. So also you should kind of find out what the shader files do. So the vertex shader and the fragment shader. Now if you open your solution up in code blocks, so you probably also need to change this create cube method a bit. If you didn't include the color here last time, then you might want to have it now and have kind of a darker color and a lighter color for specific vertices of one cube, such that one face is dark, other face is light, and the colors will be interpolated across the other faces. And for the splades, make sure that the faces towards the center here will be darker, and the faces towards the end will be lighter. So that's also important. Now if you look at the others folder here, down here, then you find the fragment and vertex shader. Now we already saw that they will be they're loaded in from this line, right? So let's open them up and see what's there. So here we have some kind of uniforms. In the task submission you should say what those uniforms are. Now we have a projection, view, and model matrix, and also those are matrix 4s, and also there are those in and out variables. Now those you need to also specify in the solution what those mean, what do they do. And in those we have the position, color, and some interpolated color value. This interpolated color value gets assigned the color value, so figure out what this does. And in the GL position, what we're doing is we are multiplying the local position of a cube by model matrix, so taking it into world space, then into view space, and then doing the projection. So what this means is that if you have your cube modeled in some local space, right? So you have vertices here, 1, 1, 1 with coordinates in relation to that coordinate system. But now you have some kind of a scene, a world, where there is another center of the world coordinate system. And in that coordinate system, in world space, the coordinates of this vertex here might be completely different. So I don't know, maybe some 10, 4, and minus 2. So because the cube is positioned in a certain place in the world. And so the matrix that transforms the local coordinates into the world space coordinates is called the model matrix. And after that we have somewhere in our scene a camera. This camera also has its own coordinate space in the center. And to make the transformation simpler, then there is also a transformation that now takes the world space coordinates and transforms them into this camera space. And that transformation is called the view transformation, so it has the view matrix. It's not the same as the camera matrix, it does the opposite transformation. So in the end, like those coordinates will be represented in relation to the camera space, in relation to the camera's origin and so on. And finally, a projection is performed on those coordinates, resulting in either a perspective projection or an orthographic projection, depending on what this matrix actually is. So what we have is a vertex, a model matrix, a view matrix, and perspective or the projection matrix. Sometimes those matrices are multiplied together into a single matrix, or those two together in a single matrix. So this would be called a model view projection matrix. So depending on like how many or what exactly is multiplied. So when it's a model view matrix, then only those two are multiplied together. When it's a model view projection matrix, then the projection matrix is also there. So the operation you need to do in your vertex shader may be a vector times a matrix times a matrix times a matrix, or a vector times a single matrix. So of course the latter is more optimal. Right, this is exactly what you can kind of see here. So currently there's this position, it is converted into homogeneous coordinates. So we add 1 in the 4th dimension to make the translation possible, and then we multiply it with 3 matrices and get the resulting position. And the fragment shader is quite simple, like this is what you saw before in one of the tasks as well, or if you have opened this file. So we just output a color, and that will be whatever is this interpolated color has. So figure out what does this mean, what does this do, and what color do the fragments actually get. And if you assign like different colors to your vertices in this create cube method, then you should see the result. So don't forget to comment and write your knowledge about the subject in the task submission, and have fun.